All right, so this is part 2 of our electrochemistry videos. And then this video is actually going to be pretty short. We're just going to kind of briefly look at some notes on batteries, okay? And, you know, batteries are pretty interesting things. They are a tremendous source of toxic waste, but could also be pretty useful in terms of their electrical capability. I think we all would agree with that. So, a couple of notes here I want to make sure we cover. But again, this should be a pretty short video. So let's just hop right to it. In here. All right. So the application of electrochemistry is, again, typically utilized in batteries. And a battery is a self-contained electrochemical power source that is either one or more voltaic cells, usually contained in steel to prevent the loss of some toxic substance. There can be primary cells, which are unrechargeable or non-rechargeable batteries. Their reaction proceeds to completion, and once it's done, the battery can't be charged. There's also secondary cells, which can be recharged. Now, one of the things that we keep in mind when it comes to batteries is that if we connect them in series, so this would be connected in series, then the sum of the electropotentials of each individual battery becomes the overall electropotential of the whole thing. So basically, it's like linking the voltaic cells together, and so these two things add up. And in this case, like in this flashlight, we have 3 total volts in our 2 batteries. Now, we'll also talk about corrosion and rust-proofing things and a little bit on the stoichiometry of electrolysis in this video. So let's look at some batteries. 4 main kind of batteries we want to be familiar with. Number 1 is the lead-acid battery, which uses solid reactants and produces solid products. So this is really great because that means Q is going to be 1, because we don't include solids in our reaction quotient. And that means that the EMF is going to stay pretty constant as the battery discharges. Now, that's really good if you are a battery in a car, right, which needs a pretty good 12-volt shock of electricity to get the engine turned over. And if the battery is cold or in some way not fully charged, we need that EMF to be constant. Now, the problem with this is that obviously a lead-acid battery is made with lead and acid, both of which are things we don't really want out in the environment. The second important kind of battery is the alkaline battery. This is definitely the most common primary battery. I think there's something like 10 billion with a B alkaline batteries made every year. They are primary batteries, which means they cannot be recharged. They need to be recycled. There's also NiCad batteries like nickel cadmium or nickel metal hydride batteries. These are pretty useful. They are lightweight, they're rechargeable, but unfortunately cadmium is toxic and heavy. It makes the battery heavy. And when you're making something like, what did I have written down here? 1.5 billion per year, you have to ship them, and the heavier the batteries are, right, the more it costs to ship, the more carbon emissions you have, the greater the carbon footprint of the product. So the fact that cadmium is a toxic heavy metal and that it increases the mass of the battery, obviously in one battery, not a big deal, but when you make 1.5 billion, that adds up. Nickel hydrides are somewhat lighter than nickel cadmiums, so they are being replaced with those. The last category would be the lithium-ion battery. These are rechargeable, they're light. This gives us something we like to call energy density. So the light lithium, the lighter the battery compared to the amount of energy it produced is the energy density, right? Mass of the battery over the volume of energy produced. Since lithium is really light, you can get a lot more lithium into a battery of the same weight as a nickel-based battery. But that lithium is going to produce a greater amount of energy, and so the energy density is higher. We usually see lithium-ion energies in things like laptops and cell phones and that kind of thing. The typical of a lithium ion cell is going to be something like 3.7 volts, right? For a nickel, or actually, I don't have that one in my notes. I do have for an alkaline battery, typically E of the cell is going to be about 1.55 volts. And then for our lead acid battery, this is 12 volts. And the lead acid batteries that we use in our cars, they look like this thing here on the left. They have a lead grid filled with what we call spongy lead. That's our anode. There is, that's the red guy here. The blue is the lead grid filled with lead oxide. That's our cathode. And this thing is entirely submerged in sulfuric acid, which is our electrolyte. Now, it's important that these red and blue things do not touch. And so you can see all the blues are connected in series to this anode right here, this cathode right here. All of the reds are connected to our anode right there. And they only touch when you bridge this circuit. Now, in order to keep them apart, they sometimes put glass or they put wood in there. Right? Either one can keep those plates, those grids apart. Now, all of these, each one of these little combinations produces about 2 volts each. And you usually have 6 of them in the battery, so 6 times 2 volts each gives you about 12 volts. If you are testing your car battery to see if it's charged or if there's something wrong with it, it should probably read 12 or 13 volts, something like that. I think the official E of the cell for one of these, according to your textbook, is 2.041 volts. So it should be slightly above 12 if there are 6 cells in your battery. Now, for an alkaline battery, this is the cathode is this manganese oxide graphite combination. The anode is zinc and concentrated KOH. This is the alkaline in the alkaline battery. This is usually steel, all right, and that is to prevent the KOH from getting out. Right? We don't want that to happen. In a lithium-ion battery, it actually works a little bit different. It has to do with the fact that you can get lithium to fit in between these layers over here on the right. But basically, the anode is comprised of lithium and graphite. There is an electrolytic solution in the middle, a more gel, and then there is this cathode on the right, which is cobalt oxide. So cobalt is the blue, red is the oxygen, and the lithium can kind of stack in between those. You can get the lithium to go back and forth, and so this is a rechargeable battery. Now, a fuel cell is similar to a battery, except for the fact that batteries are self-contained. Fuel cells have to have a source of energy or a source of fuel continuously provided. Now, fuel cells typically would be classified as less efficient than a battery because what a fuel cell does is it converts the thermal energy of combustion over into electrical energy. So if you were to burn something and use that heat to convert water into steam, and then the steam turn an electrical generator or turn a turbine, which would turn an electrical generator. The problem with that setup is the fact that the conversion of thermal energy to electrical energy is usually only about 40%. There is one exception to that, which is, or at least one exception that is regularly used, and that is the hydrogen fuel cell. So in this cell, hydrogen and oxygen are converted into water. These cells are about twice as efficient as combustion, so something around 80 or 90%. And the cells are going to use hydrogen as the fuel and oxygen from the air in order to drive this cell forward. Now, NASA actually uses the hydrogen cell in a basic environment in order to power the electrical stuff on most of its space stations. And the cool thing about this is if you look at the cathode anode reaction, you end up with 2H2 plus O2. This is a gas, and this is a gas. These two things are stored on board the spaceship, the space station, whatever. And when they react, you end up with 2H2O as a liquid. And the astronauts actually drink that water. So the production of this voltaic cell or this fuel cell rather, is useful to the astronauts, both because it powers many of the things on the spaceship, it creates electricity, but it also provides their drinking water. So that's a pretty useful application of this fuel cell idea. Now, corrosion is oxidation, or is a redox reaction that gives us a metal corrosion converts a metal into an unwanted compound. There we go. And often damages whatever it is that is being corroded. These are undesirable redox reactions. Let's say you have like a shovel and you get, moist dirt on the shovel and you leave it there, you'll notice that it starts to pit. And that pitting, those spots, are caused because the iron in the shovel is being oxidized, all right? And the electrons from that iron is going to migrate over to some region, probably wherever the oxygen is in contact with the shovel. And that's going to, cause reduction. And that reduction is going to produce rust, right? Fe2O3. Now, you'll probably notice that the rust does not form here where the water is, but rather where the oxygen is in contact with the shovel. If you want to prevent that, you can do a couple things. A lot of times what we do is called like cathodic protection, which is where we're going to coat the shovel, if it's a shovel or whatever it is, with something that oxidizes more easily than the iron does. So like the zinc in this case. And the only way the the iron underneath could rust would be if something damages the zinc, and like in this case we have a chip here that's gotten all the way through the iron, or if you completely get rid of all of the zinc that is on the top. And so that's like an example of a sacrificial corrosive. So we let the zinc corrode, and that protects the tool underneath. Now, another way that we can do that, this sacrificial anode, is with pipes underground. We can use magnesium for that. We just solder it right to whatever the pipe is underground, and that sacrificial anode, that magnesium anode, is going to be oxidized before the pipe. All right, so they just check it every now and then and replace it as needed. Electrolysis is another application that we can kind of steal from voltaic cells and the understanding of how metals are deposited onto our anodes and our cathodes. And this would be an example of a non-spontaneous reaction in electrochemistry. And in order to get this reaction to occur, we actually drive it forward with electricity. And that's what makes it electrolysis. So if you want to plate something, like, let's say you want to plate nickel onto steel like they have in this picture on the right, or if you want to, whatever you want to plate, we use electrolysis to get that to happen. Now, the stoichiometry behind electrolysis is pretty simple. Use these 4 little bubbles on the right. So we're going to take the quantity of charge, and we're going to use Faraday's constant to convert that over to moles. Moles of our electrons can be converted into moles of substance oxidized or reduced using the balanced half reaction. And the formula weight can then convert moles of your substance into grams of substance. So you can actually calculate how many grams of oxidized or reduced substance you will make given some quantity of charge. Use this equation here we got on the left. Q equals, I can't remember if that's, I believe that's L. No, I, sorry. IT equals NF. Q is the charge in coulombs, I is the current in amps, T is time, and in here is going to be the moles of electrons, which is different from the Nernst equation. It's not the number of electrons, it's the moles of electrons, and F is still Faraday's constant. So we can use that to calculate our charge there in coulombs. So once you have Q, you can just step through a little bit of stoichiometry and get however many grams or however many moles of oxidized substance are reduced. Or you can work the other way, right? Say I want to make 12 grams of this whatever. How much charge do I need? I go the other way. So again, we're not delving too deep in electrolysis into corrosion or anything like that, into electrochemistry as a whole. We're just kind of scratching the surface. If you have questions about this, reach out, let me know. I'll be glad to talk about it with you. But other than that, I will see you guys in the next video, which will be on some practice problems. All right.